Let me ask you a quick question. If you had to guess, which NASA facility would you say has the most rocket launches every year? You might think Kennedy Space Center in Florida, right? It's not. It's actually right here on the eastern shore of Virginia at NASA Wallops Flight Facility.
Yeah, the Wallops Flight Facility, it's awesome. Not only do they launch a ton of rockets here every year, but they also do critical aeronautics research and far-reaching scientific investigations in the U.S. or around the world too. All this is launched and managed on this tiny island. Hey, I'm Johnny Alonzo.
And I'm Jennifer Pulley. And today on NASA 360, we'll take a closer look at the suborbital launches that are being conducted here at NASA Wallops Flight Facility, all to help us better understand our world and our universe.
Nestled along the Atlantic Ocean, just across the road from the famous ponies of Chincoteague, and not too far from Washington, D.C., this facility is an ideal site to launch orbital and suborbital payloads. It was originally established in 1945 to conduct aeronautical research using rocket-propelled vehicles that help us better understand aerodynamic and heat transfer issues on aircraft. Some of the first tests involved strapping unmanned aircraft models onto rockets and blasting them off. Back then, there were no computers or wind tunnels that could provide enough data for us to understand the burgeoning supersonic flight industry. Pilotless aircraft tests were the main tests performed here until 1957, when the Soviets sent Sputnik into space. After that, the space race was on, so Wallops' mission changed somewhat. Soon, Wallops researchers began testing NASA-developed components of the human space program, such as capsule escape techniques, research and re-entry and life support systems, and not to mention the technologies and instruments for solar satellites, astrophysics, geospace, astronomy, microgravity, and telescopes. Since its first research launch on July 4, 1945 through today, the Wallops launch facilities have set up over 16,000 rockets that have increased our scientific knowledge.
Of course, launching rockets today is a very sophisticated undertaking. Because there are so many variables at play, researchers here at Wallops must manage each launch very carefully. To do this, all the most important information from safety, weather, communications, and launch and abort features all happen at a facility called the Range Control Center. In this building, teams of people sitting at the different consoles prepare and monitor each launch to make sure they go off without a hitch. One of the most important positions at the Range Control Center on a launch day is that of the test director. The test director takes feedback from the different team members to ensure the mission will be a success. Johnny spoke with test directors Sarah Darty and John Dickerson to find out a little more about the range facility on a launch day.
This place is really cool. I mean, it's kind of like mission control.
Yeah, that's exactly what it is.
Yeah.
It's the Range Control Center. It's a main information hub for data that we're gathering on the day of launch as we're going through the countdown and getting ready to launch a rocket.
And what's its main purpose?
We gather information here from the radars that are tracking, from the surveillance aircraft and ships, and from the rocket itself is sending us data. And we put it on a bunch of computer monitors and screens here in the center so people that need to make decisions on it or monitor status can see what's going on while we're going through the countdown and when we get to T0 and beyond.
You have some awesome screens here. Can you tell me what they represent?
Sure. We put any kind of data that we're gathering here on those screens. So we're looking at the real-time flight trajectory of the launch vehicle while it's launching so we can see its actual position in time. We're looking at weather displays, we're monitoring surveillance cameras that we have that are looking at the vehicle on the pad, or they're looking at boats that are getting too close to the coast. So we're monitoring all that, and we can change any display that we want to up here, just what's relevant at the time as we go through the countdown.
As Sarah mentioned, on a launch day there is constant surveillance happening to assure the safety of everyone involved. Launching rockets is inherently dangerous, and mission directors keep a close eye on radar and safety personnel to make sure the launch area is clear of aircraft or boaters near the launch zone during a flight. This can be a daunting task due to the sheer number of vehicles launched here every year. Everything from relatively small sounding rockets to the larger Taurus-class rockets will launch from here. To find out more about the different types of rockets launched from Wallops Flight Facility, Johnny caught up with John Dickerson.
We have both orbital and suborbital vehicles. Our suborbital vehicles are what we typically call sounding rockets. The orbital vehicles are like the Minotaur class vehicles. The suborbital vehicles, we launch maybe 2 or 3, maybe 4 a year from here, and then we have ranges outside of here that we go and launch from. The orbital missions, like the Minotaur class missions, we maybe get 1 or 2 of those every 2 years. Sure. We're currently building a new facility for Taurus 2, which is resupply the station, that sort of thing. Much larger class of vehicle.
Do you only launch rockets here?
No, we launch UASs, unmanned aerial systems. We test aircraft. We have ultra-high duration balloon facilities. We actually build and make rockets here. So we got a whole host of things that we do, not only doing rockets, but we do a bunch of other stuff as well.
Hey, thanks so much for having us at Mission Control.
No problem.
Awesome. Hey, don't go anywhere. You're watching NASA 360.
As we just saw, there is a very complex system to launching rockets. Currently, Wallops averages about 30 launches per year, with a majority of those launches being sounding rockets. Now, right now, we're inside the unique facility that manufactures many of the components and then integrates them into the sounding rockets. Let's speak with my buddy Brian Hall to find out more about sounding rockets and how they're being used here. Okay, Brian, what is a sounding rocket? How is that different from, say, like a Saturn V, a huge rocket?
Sounding rockets are smaller rockets consisting of 1 to 4 solid rocket motor stages and the payloads that allow researchers to get low-cost, quick turnaround access to space.
Okay, and in this building there's actually a full-scale sounding rocket here.
This is a full-scale model of a 2-stage sounding rocket vehicle with a representative science payload on top.
Okay, and inside the payload is?
The science instrument, along with our systems that allow them to collect their data.
Okay, so where do you find these rockets?
Most of our rockets are actually surplus military assets that were going to be accessed, and we utilize them to keep our program costs low.
So Brian, how do sounding rockets work?
Sounding rockets consist of payload and motor systems. The first stage motor is ground fired. Subsequent stages are fired during flight. And those stages will loft the payload anywhere from 30 to 950 miles and provide flight durations from 5 to about 20 minutes.
Okay, so you're talking pretty high up. Is that considered out of Earth's orbit?
Actually, they do not have enough velocity to escape Earth's gravity, so they fly along a parabolic trajectory.
Okay, and are they recoverable? Where do they land?
Some of our missions are recovered. We launch missions out of Wallops Flight Facility, and they're recovered from the water, and also out of White Sands Missile Range in New Mexico. They're recovered on land, and routinely those payloads are refurbed and reflown later for subsequent science missions.
You mentioned using surplus military rockets. Do you design or build any here at Wallops?
We actually take the surplus military motors and design a vehicle configuration from those motors.
So is this the building where they're actually designed and built?
All the design and fabrication and assembly takes place in this building. The rockets go through a very rigorous test program, the payloads especially. We're in the environmental lab facility right now where we take them through a battery of tests to make sure they'll survive the rough sounding rocket flight environment.
Okay.
And we also conduct a vast number of test flights to make sure they're going to survive the flight environment prior to using them on science missions.
Brian, talk to me about this room. What kind of testing goes on here?
This is a large concrete and steel reinforced room with a Kevlar curtain there to allow us to test any in-flight deployments or other mechanisms prior to flying them on a science mission. Payload system would be mounted on the turntable there. It would be spun up to its flight environment, and we would actually monitor through video systems the actual events, and the events are triggered safely by a technician outside the chamber.
So Brian, what are the advantages of using these smaller sounding rockets?
Because they are low cost, quick turnaround, they provide a platform for instruments to be tested on these smaller rockets at much lower cost before they go on to the bigger rockets and larger orbital satellite missions.
I had mentioned that Wallops launches approximately 30 launch rockets a year. That seems like a lot.
It is a lot, yes. Our program launches anywhere from 20 to 30 a year, depending on the science, and from locations all over the world. Our vehicle and payload systems are portable, as well as the Wallops range systems are portable, so we go where the science is. If there's a certain phenomenon, like the aurora borealis, that's common in Alaska, we'll take payload systems up there to launch and study the aurora in situ, in time and in place, while the phenomenon is occurring.
Wonderful. It's kind of like you just pack it up and go on a road trip.
Yes.
So Brian, when you're testing with these sounding rockets, do you usually test them to failure?
Actually, we test our systems to failure in the initial design phase, and then we'll test them to various qualification levels that ensure they'll survive flight.
Okay, why?
Because our program is a little bit different than NASA's primary mission, where failure is not an option, our program accepts a lot more risk because we want to keep the cost low. We want to develop new systems for larger NASA missions.
Walk us through the process of designing and building a rocket, a sounding rocket.
Our mission life cycle span anywhere from a couple of months to around 2 years. In that process, we get the requirements from the science researcher. We take those requirements, design the payload systems, pick out the vehicle, design the trajectory. Then we actually build most of the hardware in our facility here, do the assembly, and then we'll bring it to our test labs and test it and make sure it's ready for flight. Then we'll ship it out to the launch head and actually conduct the launch operations.
You said 2 months. I mean, a couple of months, that's a pretty quick turnaround.
That is a very quick turnaround. That's some of our simple payloads.
Yeah, an advantage to having these smaller rockets, yes. I suppose. What is so unique about NASA Wallops flight facility and specifically this building and designing and building sounding rockets?
We're the only group within NASA that actually does this type of work. We're very unique in the government as well. Consequently, we support not only NASA, we also support many government agencies and universities who are looking to conduct science research.
Brian, thank you so much.
It was a pleasure.
We appreciate the lowdown on NASA's sounding rockets. Stick around, you're watching NASA 360. We'll be right back.
Okay, so far we got a pretty good idea about what's going on the rocket launch side of the facility. But folks here are also working on cutting-edge aeronautics research as well.
Whether it's supporting ice studies in Greenland or flying UAVs through hurricanes, researchers here are using a variety of different types of aircraft to do cutting-edge research. I spoke with Shane Dover to find out a little more about the flight program here at Wallops.
Shane, where are we?
We're at Wallops Flight Facilities, hangar N159, home of the Airborne Science Program.
Right on, man. So, look, I see a couple planes you guys are working on back here. Can you tell me a little bit about them?
Sure, this is the P-3 Orion.
Right.
It was originally placed in service in the 1960s, 1970s timeframe from the United States Navy. We've retrofitted these particular aircraft for NASA Airborne Science.
So wait, you just mentioned that these planes are from the 60s. I mean, is it cool to use older planes?
Yeah, these planes, although they were built in the 60s and 70s, they're still in service with the United States Navy, and they'll be in service till about the year 2025, 2030. Nice. So as long as the plane's maintained well, it can fly a very long time.
What kind of missions are you doing here?
Well, the aircraft in general, we modify heavily from mission to mission. Okay. We fly a wide variety of missions, everything from atmospheric chemistry missions to the most recent deployment we did in Greenland for the Operation Icebridge.
Really?
That mission flies low altitude lasers, it uses radar systems, it uses a device that measures the Earth's gravity, believe it or not, and a magnetometer uses that suite of instrumentation to measure the depth and volume of ice. That mission is repeated year after year, and that allows us to get an idea of changes in that climate in Greenland.
Why in Greenland?
Well, Greenland represents the northern polar ice cap. Okay. Greenland's unique in that it has this very mountainous exterior, but the middle is all ice cap. So by measuring the depth of that ice cap and where that ice sheds into the ocean, we get an idea of the rate of change of the volume of that ice cap from year to year. It gives us an idea on global climate change.
Greenland's like a couple thousand miles away. Right? I mean, you guys like fly, from here back and forth? I mean, you stay there? What's the deal?
Yeah, we go to Greenland and then we operate out of two major airfields in Greenland. Okay. Thule Air Force Base and Sonderstrom, which is a airfield a couple hours south of Thule. Sure. From there, we launch about 8-hour profile missions. Okay. Those missions go out over the ice cap, make their measurements, and return to that airfield. During that deployment, we flew 75,000 statute miles. That's about 3 times the circumference around the Earth at its equator.
So tell me, why is the P-3 such a great platform?
P-3 is a heavily modifiable airplane. It's safe, it's reliable, allows us to fly those low altitude mission profiles with a very large suite of instrumentation on board, gathering the most data possible during that time frame. Then its performance capability allows us to fly into these fjords and down in these glacier regions. And then if we did have a malfunction or a problem, we could climb out of there. It has a lot of excess power, a lot of performance capability.
All right, so I mean, you're flying these larger craft, okay? What about like the smaller ones, like UAVs?
UAVs definitely have a role in airborne science, and I think an increasing role. UAVs are good because they don't put a man in the loop, especially in some of those regions you would not want to fly. UAVs can fly missions low over the ocean in the middle of a hurricane, and there's really not a risk to that particular platform. So that's the sort of mission that you'd fly with a UAV that you wouldn't necessarily want to fly with a manned platform.
Hey Shane, thanks so much for having us out here today, and good luck on your missions, man.
Thanks, Johnny. Thanks for having NASA 360 come by.
No worries. See you again.
So far, we've seen how Wallops researchers are using different types of rockets and aircraft for scientific study. But get this, they're also using high-altitude research using one of the oldest flying devices known to man, the balloon.
I spoke with Debbie Fairbrother here at the Balloon Program Office to find out more.
NASA does scientific research on high-altitude research balloons. The balloons that we fly are a low-cost, quick response access to near space. So they're similar to a satellite-type mission without the expense of a rocket launch and getting manifested and the time duration. We can support universities with grad students. They can work on an instrument from the origins up to building up in flight and get their data within their PhD.
That's fascinating.
It really is. We basically can fly large science instruments to about 120,000 feet, which is above 99.9% of the atmosphere, for durations of 1 week to a month or so. And our target is to fly for up to 100 days.
Let's get down to the basics here. How do you get these balloons off the ground? Where do they go? And how do they fly?
Basically, we put the amount of helium in them that we need on the ground. We have a launch crew that'll lay out the balloon with a parachute and then the payload. The flight train at launch sometimes is up to 1,000 feet. So once we let it go, the balloon, the gas is in the balloon, the helium expands and expands and expands until it's finally fully inflated at float, which is typically between 110 and 130,000 feet. Okay. Now think planes fly about 30 to 40,000 feet. So we're way high, 99.9% of the atmosphere we're above. Essentially we fly with the wind, so Mother Nature's in charge. So we have meteorologists on staff that are looking at the wind forecasts and understanding the patterns of the winds at the different times of the years that we fly so that they can predict where the balloon will go. We can take with our 40 million cubic foot zero pressure balloon, which is made out of 0.8 mil film. An example is right here. That thickness of material. We can lift about 6,000 pounds to 130,000 feet.
Underneath this balloon.
Right.
Okay, so again, more perspective. 6,000 pounds is about?
A car or two.
A car or two.
Sure. It depends on how big your car is.
I mean, this is so thin. This is amazing.
Yeah, so we have to do some special testing to make sure that it can handle the really cold temperatures as you go up through the atmosphere.
And then what about this payload that you're talking about? What the payload's underneath this balloon, the balloon is flying via Mother Nature.
With the wind.
Okay, with the wind. How are you seeing what's going on? How are you monitoring that?
Sure. Within line of sight, we get high data rate back from the instrument. But once we leave the local area where we launched from, we use the satellites. We either fly Iridium or TDRS communications, so they basically go from the balloon to the satellite down to the Earth. And so the scientist is getting their data, or at least some of it, as the balloon flight's going on. They can make changes to the flight software if they need to, so we're constantly monitoring these balloons. When we fly an LDV or long duration flight from Antarctica.
Which is how long again?
Anywhere from a couple weeks to the longest we've flown is 42 days. And usually the limiting factor isn't the balloon itself. It's that the science is either over or they're at a good place for recovery and they want to get their instrument back so they can refurbish it. So at the end of the flight, we can send a command to separate the bottom of the balloon from the top of the parachute. And so the payload comes down on the parachute and impacts the ground, and then the balloon comes down and is collected and destroyed.
Okay, so we have this balloon, and underneath it is this payload. What type of experiment, science is going on?
It's typically space science research, either telescopes looking out into space or detectors collecting particles from space. We also have some earth science missions, and we are a good test bed for education outreach as well as for technology demonstrations.
Debbie, you mentioned the United States as a place where these balloons fly. Where in the United States?
We fly from Fort Sumner, New Mexico and Palestine, Texas. And then internationally, we fly from Sweden or Australia and Antarctica. It all depends on where the science need is. And so we support campaigns where the science needs to be flown from.
And you go there?
Yes.
What's next? What's next? You're going to take this super pressure balloon and you're going to fly that.
We're going to fly it. The next balloon that we're going to fly is a little bit bigger than we flew this year. It's targeting 5,000 pounds to 110,000 feet. So of course our scientists always want a heavier payload to a higher altitude. So the ultimate goal right now is on the order of about a 26 million cubic feet in volume superpressure balloon. And so that system would be wonderful for mid-latitude flight. So when we fly from either Brazil or Australia, we'll be able to circle the globe essentially at a constant altitude. So that's our goal, is to basically provide a stable platform for the scientists.
Debbie, these balloons are made with this material you've shown us, very, very thin. How are they kept together? I see these ridges in the balloons. It kind of looks like a seam.
Right, exactly.
What is that?
So each gore, or each segment, is a specific gore. And there's a plant in Texas that has tables as long as we need them. The plant itself is 800 feet long by 50 feet wide. And so if I need a balloon that's 660 feet, they've got a table, or a segment of tables that's 660 feet long. And basically the crew walks down and melts the material together.
It's not stitched together to form these seams.
Right, it's not
welded.
sewn. It's basically melted or heat sealed together. So you'll see this darker piece right here. This is our seal. And so they basically have the machine that does it, that they walk down the table.
And it's so strong that it keeps these balloons in flight for that duration, carrying that much payload.
Right.
That's just amazing to me.
It's fun.
It really is. Debbie, thank you so much. We really appreciate it. So Johnny, as we've seen, right, this tiny island is a major player in the science game. And in the near future, we're going to see many more launches, including LADEE, the science mission to the moon.
Wallops will also see new launch facilities that will allow the tourists, too, to resupply the International Space Station. In fact, whether researchers want to go low over the ocean, to the moon, or anywhere in between, Wallops will get them there.
And so with all this going on, it's easy to see why Wallops is so proud to have a prominent role in NASA's future exploration.
That's right. Hey, that's it for now. I'm Johnny Alonso.
And I'm Jennifer Pulley. We'll catch you next time on NASA 360.
Okay, so far we've got a pretty good idea about what's going on the rocket side of the facility, rocket launch side of the facility. Yep.
Absolutely.
Thanks a lot. Yeah, right. A lot of racket in my brain. So with all this going on, it's easy to see why.
Not just me. Not only do they launch a ton of rockets here every year, but they also do this critical aeronautics research and, sorry, one more time. When you think about sending rockets up,
as we just saw, there's a very large, Currently, Wallops. That's funny, isn't it? It's funny.